Hello everyone, welcome back to the channel Data Science with Harshit. So this video marks the beginning of another series that we are doing. So we're doing a series on computer vision with TensorFlow, and this is going to be a 4-part series where the first part would be on some very basic examples. We'd see how we can train a very basic model, one layer, one neuron network, and then the second example would be training over a fashion MNIST dataset where we'll try to classify images into different type of apparels. Then the second part would be on convolutional layers and convolutional neural networks, pooling layers. The third part would be using image augmentation, image data generators. And the fourth part is the final part where we'll be using pre-trained models to classify some real-world images, complex data sets. So this is the first part where we'll be looking over some very basic examples of predicting house prices with the number of bedrooms that are given, and the second part is, as I told you, is the fashion MNIST data. So without any further ado, let's get started. Now, to get a very basic understanding of how deep learning, or more specifically how neural networks work, what we're going to do is we are going to create or solve a very simple problem of house prediction. Basically, we would be predicting house prices based on the number of bedrooms. So it's basically just a simple linear function that our model should learn. So we're going to see how we can implement this very simple neural network with only one neuron and one layer, and let's see how it learns that pattern and predicts based on the input that we provided to the model. And then later on, what we're going to see is we're going to dive into some computer vision problem, look at the fashion MNIST data, and then try to predict and classify each of those images based on the pixel intensities, and seeing how we can create a dense neural network to predict or to classify a particular image as one of the items in the clothing department. So the first step is to import TensorFlow and Keras. Again, we're using Keras from TensorFlow itself. So the convention is that we import TensorFlow STF, again separately imported Keras here. So let's check the version. Make sure that you check the version of your TensorFlow library. So here we have 2.3.0 TensorFlow, and checking the Keras version. So here Keras API basically is at 2.4.0. Alright, then we have imported NumPy and Pandas just in case we need some data manipulation tasks. So we'd be creating dummy data. So for here we need NumPy. So as you can see, I have created basically a dummy data following a simple linear equation. Basically, I have added some number of bedrooms of different houses. So let's say in my bedroom underscore x, I have created a NumPy array, which is basically a 1D array, and then I have added the number of bedrooms of each of the houses that I would have in my data. So the first house has 2 bedrooms, then the second house has 8, 4, 5, 6, and so on and so forth. Now the formula here is the house price depends on like 50,000 for 0 bedrooms. Basically the constant is the C is 50k, and mx is basically then I have 50 star the number of bedrooms, so that would be bedrooms. So this 50k would be the additional amount that you'll have to pay, and the rest of the cost of the house would depend on the number of bedrooms. Basically we have, it would be like 50 times the number of bedrooms that are there in the house. So this would determine the cost of our house. All right, so as you can see, according to this formula, I have created the house prices as well. So for a 2 bedroom house, 2 BHK apartment, you can say 150K is basically what the price would be, following the same formula here. 50 into 2, 100 plus 50, that is 150. For 8 bedrooms, I have the cost as 450. Again, 58 into 50 into 8, 400, and then 50, so on and so forth. So this is basically how I have created my dummy data. Let's run this cell as well. So our dummy data is now ready. Now the next step is the very important step here, where we are going to create a very basic and very simple neural network. Now this neural network contains only one layer. So again, I would emphasize here that if you want to get a refresher, a basic understanding of what a neural network is, or how a multi-layer perceptron, or what a basic perceptron is, how do you train a perceptron. So we won't delve into the mathematics part of it because that's beyond the scope of this video. But you can definitely go ahead, and there are a bunch of resources on Coursera, on YouTube as well. I would recommend you to go through the Andrew Ng course on deep learning, that basically talks about the basics and what's the mathematics that goes behind all of these models. So you should go ahead and look at that. For this particular series, we would be focusing on the implementation, the coding part of it. So I would talk about each of the keywords that we would be using, functions, and what's actually happening behind the model. But we won't be diving into the mathematics or the calculus that would be happening behind the model in order to train it. So how does a gradient gets calculated and all of those things. You can learn it from certain books that I'll add the link to in the description, and I'll add the link to Andrew Ng's course as well, which is free of cost. Here you can see we have the model definition. So the model definition, basically this is we are using the sequential API. Now this API basically allows you to stack one layer on top of another, and that's how you can create your dense or any sort of neural network. So the sequential API, what it does is it takes in different layers. So the keras.layers.dense, so we are basically, this is a dense layer that we have created. So this would be a hidden layer. So we have an input layer where from which we'll have which will consume the input, and then we'll have an output, and in between we would have one hidden layer. So this is that hidden layer. So we would have the input. The input is simply 1D array. So that's why to this dense layer, what we have to provide is we have to provide the input shape of our input. So this is a 1D array. So that's why you can see the input shape is 1. And then units. So this would only need one neuron. So one layer, this is the only layer that we have in our sequential model. And we have only one layer and only one neuron, that is 1 units. So this is the simplest model that we can have, very simple, again using TensorFlow. So let's run this. I have stored this model in the model variable. So you can check the summary of the model. So once your model is defined, you can check the summary, like how many layers does it contain, what are the number of parameters that needs to be trained, what are the number of parameters that cannot be trained, that are non-trainable, and number of dense layer. If there is any other type of layer, we have only added dense layer here. If there is a convolutional or pooling layer or any other sort of dropout or any other layer, basically this summary would tell you the entire give you an entire snapshot of what the model basically contains. So our model is simply one dense layer, and we have an output shape of 1. This would basically return one output based on the number of bedrooms that we provide. So this model is actually required to learn this function that we have defined. So this equation should be learned as close as possible by the model. Now, the next step would be to compile the model. Now, how would our model learn? How will we train the model? And how will we measure the loss? Basically, what's the error in our prediction, comparing it with the actual data. So you can see that in the line model.compile. So this is how we compile a model. Now this compile function takes two important parameters, two important attributes. One is the optimizer and the second one is the loss. Now, if I tell you what's actually happening here, so the first thing is that how does a model work? How we train a model? So our model, we provide the data to it. Now the data contains both the trainable the features and the target variable, and it tries to map the relationship between the data that we have provided and the target variable. Now, initially, the model doesn't know what's the relationship, so it has to guess like what would be the output of a particular instance. So it guesses. Now then, after the guess is made, the loss function tries to measure the error between the actual value and the guess that the model has made. Now, based on this error value, it then tries to improve upon it using the optimizer. So the optimizer will basically try to improve the result of the model, and accordingly it would keep on moving forward. So again, it would make a guess, and the loss function basically would again measure the error in the prediction. So the logic is that optimizer will try to improve the score, will reduce the loss, and the loss function will keep on calculating this error and send it back to the optimizer, and then optimizer would basically improve this score, make another better prediction if possible. So this is how loop is going to be run, and we're going to train this over 100 times and see to what level of accuracy or to what level of loss can we get. So this is basically what's happening behind this compile model. There's a lot of mathematics that's going behind. So this SGD basically stands for stochastic gradient descent, and what's actually happening is it tries to calculate the gradient at every step, and then tries to converge the model to a particular solution. So that's how this model is being trained using the backpropagation algorithm. All right, and the mean squared error is how we are measuring the error in our predictions, in the guesses that the model is making. So this is how we compile the model, and then the next step is to fit, or you can say to train the model. So we are training the model 100 times. So the epochs, they basically denote the number of times that we want to train, and we have provided the bedrooms data and the house prices, which is our y. So let's run this model. So this will run 100 times. So you see that the loss has been decreasing. So it started from 60 or 70 something. It started from 77, and it reduced to, the last value was 48 point something. So now what we're going to do is we're going to predict what the value is for 10 bedroom apartment. So what would be the house price prediction made by this model for a 10 BHK? So let's do, so the function is simply predict, model.predict, add the value in an array. So in this list, so this would make a prediction. So for a 10 bedroom apartment, the cost would be 563,000 US dollars. That's what the model is saying. Basically, the actual value, as you would find out, that the actual value is 550K. So there's some error in this. So accordingly, you can also provide validation data alongside and check the accuracy of the model. So yeah, this is how you train a very basic model. Now the next step is to look into a more complex problem. We're going to dive into computer vision and then check how we can classify images. So for the image classification example, we are going to use the fashion MNIST data. And we're going to use Kera's utility functions to fetch and load some of the common data sets like MNIST and Fashion MNIST. And the dataset contains 70,000 grayscale images of apparels. So basically, these are images of ankle boots, images of t-shirts, trousers, sneakers, pullovers. So there are a bunch of items. So in total, there are basically 10 classes that all of these images are classified into. Now, our aim here is to develop a model that if given an image, it should be able to classify what sort of apparel it is. So let's start off by importing the data set. So we're going to import the data, fetch and load the data from Keras. So Keras provides some utility functions to do that. So first of all, we have created an object, instantiated the Fashion MNIST class, and it has this load data function that is available, which what it does, it splits the data into training and testing. So we basically have xtrain, ytrain, and xtest, ytest. All right, so now that the data is loaded, the next step is to look at how much or how many instances are present in the training set and how many instances are present in the testing set. So xtrain.shape, shape would give us the number of instances. We have 60,000 in training set, and then we have almost 10,000. Yeah, 10,000 because total in total we have 70,000. So 60,000, 28 by 2. So all of these images are basically 28 by 28 pixel images. Again, let's look at one of the image. So this, you can see all of these images basically have intensities ranging from 0 to 255. So this is one example of the training set. Now let's look at ytrain for first instance. So let's look at for the first instance. So you see we have the label as 9. So this would basically correspond to one type of apparel, and by looking at the dataset description, you can look it up. I'll add the link to the dataset in the description below. So 9 belongs to ankle boot, the index 9. So it's starting from 0 to 9. So there are total 10 classes here. So we are reserving 5,000. We don't have validation data here. We only have training and testing. So we are reserving 5,000 rows. Next step is to reserve 5,000 rows for validation. And that's what we're going to do from the training set itself. So as you can see, we are simply using slicing to reserve 5,000 rows, the first 5,000 from the training set. So since we are going to use gradient descent for the model training, we should be scaling our features. So that's why we have converted the intensities into 0 to 1 range and divided them by 255. So first 5,000 for validation, and then again doing it for the labels as well. For xtest as well, we'll have to scale the images in the testing set as well. So run this. These are the labels that I have picked up from the dataset description. So t-shirt, top, trouser, pullover, and created a list out of it. These are my class names. So now if I want to check for all the labels, so the labels are in integers. So if I want to check what was ytrain 1, so the label of the second image, so that is a t-shirt slash top. And also we can try to plot or look at these images, what these images actually look like using matplotlib. So let's do that for xtrain, the second image. This is t-shirt top. So let's try to plot the image. So you see this is the t-shirt top that we have the label for. So this is what our image is basically looking like. So again, using the image show function from the matplotlib library. Color map is binary. It's grayscale, black and white. I have switched off the axis, and this is the image. Again, if you want to look at a few, so this is basically the code for plotting a few items. So here I'm using subplots to create a range of images, basically plotting from 0 So these are the 40 images which are divided into 4 rows and 10 columns, and then I have run a loop to get an index and plot them in this particular format. Again, very simple. If you'll go through it one by one, you'll be able to figure that out. Added some white space and some horizontal space to display them in a nice manner. All right, so these are the images. I have added the labels as well. So these are just a few sample images. Again, now let's get back to the main part here, which is the model definition. So here again, we're going to create a sequential model using the sequential API, and this contains a sequence of layers, which are basically the first layer is the flatten layer, which is used to, since all of these images are 28 by 28 and the model takes a single tensor, so we'll have to convert this into a single tensor. So the flatten basically takes this 28 by 28 images and then creates it into a 1D array of 784 elements. So this is our input flatten layer, and then from the flatten layer we go to the first dense layer, which contains 300 neurons and an activation function. So this activation function is basically providing some element of non-linearity. So here you have to keep in mind three very important steps. The first one is, while the model is being defined, you initialize the weights, you add the bias term, and then you provide some non-linearity. So this non-linearity too is basically provided by the activation function. Now there are different types of activation function that we can use. So here we are using the ReLU function, which basically returns x for any value of x greater than 0, and for any negative value it will return 0. I'll put the function here on the screen somewhere. Alright, so then again I've added two layers, two dense layers. One is 300, these are two hidden layers, 300 neurons, 100 neurons, same activation function, and then the last output layer, which contains an activation of softmax activation, because this is multi-class classification. And then I have 10 classes, so I have 10 output neurons for our model. So this is the entire structure. Let's run this. So we can actually look at the layers that we have defined using the layers attribute. So this is my flattened, dense, and 3 dense layers. Then I can look at the model summary as well, as we saw earlier. So yeah, this is my model summary. Dense 5, dense 6, and dense 7. 784 elements, output shape as you can see. Parameter 0. Here we have 235,500 parameters. Why so? Because we have 300 neurons. So these 300 neurons would basically train over 784 elements coming out of the flattened layer. So that's why 235,500 parameters. And then we have 100, basically 30,100 parameters, and then the output layer. Alright, so these are the total number of parameters. This is the model summary. So for the first layer, you can also check the first layer, second layer, so that's the list. And we can check the name of the hidden layer. So that's our name. So you see this is the dense 5. We can also check the weights and the biases that the model or that particular layer has. So if we check the first layer weights, so these are the weights, initialized weights for the model, and the biases initialized by, so all the bias terms are basically initialized with 0. So that's the model that we have defined. The next step again would be to set the loss optimizer and metrics. So again, we're using the sparse categorical cross entropy loss function. So because we have sparse labels, that is for each instance, there is just one target class index. So that is indexing from 0 to 9. So the class is basically exclusive. That's why we are using sparse categorical cross entropy. And optimizer is again same, SGD. We're using the stochastic gradient descent. And matrix is, we have provided an accuracy matrix here as well. So let's compile the model, and we're going to provide the validation data as well that we have created, and we're going to train the model for 30 epochs. So that's the model training process that would start now. So this would take a few seconds. So if you see, we are getting the accuracy, that is the training accuracy, and then we get the val accuracy, which is the validation accuracy. So that is being calculated over the validation data that we have provided. So the model is being trained on the training set, and that's our validation accuracy, and it's being checked side by side. So the validation would always be a little lesser because that's the unseen data for our model. And yeah, so if there is a huge difference between your training accuracy and your validation accuracy, then that basically points towards overfitting. So the next step is to evaluate the model. So we are going to evaluate the model on our testing set. We are not doing any hyperparameter tuning, but ideally we should. So you can basically go ahead and you should check for other optimizer, other loss functions, any other number of neurons that you can find, other activation functions. You can do that and then recheck if you would be able to improve upon the validation and the training accuracy. That would be good. So hyperparameter tuning is again a very important part of the entire process. Now we are going to evaluate on testing set. So this is what our accuracy is turning out to be. This is 88%, and let's try to plot the accuracy using the history of the model training. So we get that from the history attribute. We have converted it into a data frame, and now let's plot whatever metrics that we have. We are going to plot the loss, validation loss, and training accuracy and validation accuracy. So you see that there's a slight difference between the training and validation accuracy, and then we have the validation loss is slightly higher as compared to the training loss. So you can plot these to learn about the history of your model training process. Now what we're going to do is we will predict the results for a few sample images. So from the testing images, just to see how it is predicting. So we have picked up first 5 sample images from the testing set, and we'll provide it to the model predict function and try to find out what would be the probability for each class. So let's find that out for the first 5 images. So for the first 5 images, you see that these are the probabilities for each class. So for the first image, we have 0.99 for the last image, basically the last class, that is for ankle boot. And then we have 1 for the third index, and then you can see we'll have to figure that out based on the class names that we have defined. So let's do that. So model.predict classes x sample. So this would be our predictions, 9, 2, 1, 1, 6. So this will basically give us the predicted class itself. Here we will actually getting the probabilities. And now based on these indexes that we have got from the predictions, we can actually use the class names and find out what the predictions were. So these are ankle boot, pullover, trouser, and then shirt. So let's try to compare it with the original value. So ankle boot, pullover, trouser. So all of those sample predictions have been made rightly. They were made accurately. So that is the last part of this particular example, but this is just a starting point for our journey in computer vision. So this is just a very simple, very basic example. Now we're going to build over this example and try to classify real world images and see how we can use complex models, pre-trained models to classify very complex data sets, very complex images. So I hope you found the video useful and learned something new today, and if you do, please give it a thumbs up. If you have any queries, any doubts, feel free to comment down below. I'll try my best to reply. And yeah, the next part would be coming out really soon. But yeah, you can look at the collaboratory notebook. I have added the links in the description. I've added the books that you can read. I have also added the course descriptions, the courses that you can look at in order to understand the mathematics that goes behind these neural networks. Again, we are focusing on just the coding part of it, just the implementation and learning and trying to get an intuition of what's actually happening behind these models. But yeah, this is more towards the implementation of these models and not too much on the theoretical side. So again, for that you can refer to these books, and yeah, I'll catch you guys in the next one. In the meanwhile, keep learning data science with Harshit.